Hi, we continue chapter 7, and in this part we'll be talking about the finite expansions. Now let's forget a little bit what we spoke about, what we talked about in the formulas of Taylor-Young, Taylor-Lagrange, and Maclaurin, and let's forget the expressions that we obtained in there, so we don't confuse the two concepts. And let's start over by talking about the finite expansions. So I would say that if f is a numerical function defined on a neighborhood of a point x0 nr, so we have f that is defined in x0 and a little bit around x0, so we say that f has a finite expansion to the order n at the point x equal x0 or at x0 if there exists a polynomial function Pn of x minus x0 of order n such that for all x in the neighborhood of x0, n of x0, you have f of x is equal to Pn of x minus x0 plus x minus x0 to the power n epsilon of x. So the polynomial Pn of x minus x0 is a polynomial of order n, and the function that's in here is a function that goes to 0 as x tends to x0. That's why Pn of x minus x0 can be written as c0 plus c1 times x minus x0 plus c2 x minus x0 to the power 2, etc. plus cn x minus x0 to the power n. So it's a polynomial in x minus x0 of degree n, where all the coefficients c0 to cn belongs to R, and epsilon of x is a function that contains x and that goes to 0 as x tends to x0. So Pn x minus x0 is called the regular part of the finite expansion, and x minus x0 to the power n epsilon of x is called the remainder. Now if you replace x minus x0 by h, we will have something like f of x0 plus h is equal to Pn of h, so this is x minus x0 plus hn epsilon of x0 plus h. Now as I said, let's forget what we discussed about the Taylor expansions, because in here we are starting over saying that if a function can be written as a polynomial plus something that goes to 0 as x tends to x0, we call this a finite expansion, even if this expansion is not written as the expression given in the Taylor expansion. That's why I said let's forget about the Taylor expansion. So you can have a polynomial in here that is not really f of x0 plus x minus x0 times f prime over 1 factorial 1, etc. So it might not be exactly what is given in the Taylor expansions. That's why I said let's forget about them. So now, starting over, we are saying that a function, if it can be written as a polynomial of x minus x0 to a given power, to a given order, plus a term that goes to 0 as x tends to x0, we call this a finite expansion of the function. Okay, let's say if we take the function f of x equals to 2 plus x plus 4x3 minus x4 cosine x, if we take this function, it's written as a polynomial part function, so it's a p3 degree 3 of x minus 0, right, plus a part that is written as x minus 0 power, I'm taking power 3, times x cosine x. So if we take this as epsilon x goes to 0 as x tends to 0. So if you look at this expression, it's a polynomial power 3 plus x3 times epsilon of x. So if you look at it, this expression is a finite expansion because it's a polynomial degree 3 plus x is 3 times a function that goes to 0 as x tends to 0. And it's not written as the forms that we had before, maybe. I'm saying maybe because we don't have another expression for f to compare the f prime and f double prime. Also, the function 1 over 1 minus x, as we said before, it can be written like this, right? So it's a regular part, a polynomial of degree n of x minus 0, plus this part, and this part can be written as xn times x over 1 minus x and this term goes to 0 as x tends to 0, which is the epsilon of x. Of course, you should notice that the degree of the polynomial n in here is the same degree of the xn which is in here. Okay, which means that you can have something like 1 plus x plus x4 epsilon x. That's not a problem, because you can assume that your polynomial part can be written as 0x2 plus 0x3 plus 0x4 plus x4 epsilon of x. Okay, but you cannot have like something that is that looks like this, for example. So plus x plus x2, for example, plus x epsilon of x. That's not true. That's not good, because you have a power 2 in here and a power 1 in here. We can also write the function 1 over 1 plus x in the same way as in here, replacing x by minus x. So we will have this expression as the regular part and this in here the remainder. Of course, epsilon of x in here is also equal to x over 1 plus x. So let's check this remark. If a function f has a finite expansion to the order n in the neighborhood of x0, then it has a finite expansion to the order p in the neighborhood of x0 for any p less than n. Of course, because if f of x can be written, I'm taking an example like 1 plus x2 plus x3, let's say, plus x3 epsilon x, then of course I can write it f of x equal to 1 plus x times x plus x2 plus x2 epsilon of x. So if you write like this, you will have the new regular part, which is a polynomial of degree 1 of x minus 0, and you have plus x times this new part, I will call it epsilon 1 of x. Okay, so this epsilon 1 of x goes to 0 as x tends to 0, because all the terms goes to 0. So you are able to write f in a finite expansion to the order 1. You can do so for any order less than the order that you had in the beginning. Okay, so if you have a finite expansion to the order n, you can always write a finite expansion to an order, any order less or equal to n. Then the existence of a finite expansion to the order 0 in the neighborhood of x0, it means that the function can be written as c0 plus x minus x0 epsilon of x. So if you go to the limit as x tends to 0, this term will go to 0, and you will obtain that the limit of f of x when x tends to x0 is equal to c0. So the first term that you have in here, the constant term, is the limit of f as x tends to x0. So if you have a finite expansion to the order 0, it means that the limit exists at x0 and it's equal to c0. And of course, if this limit is equal to f of x0, it means that the function is continuous. Then the existence of finite expansion to the order 1, it means that f of x can be written as follows, right? And if f of x can be written like this, it means that if you calculate the derivative of f, for example, it will be equal to 0, which is the derivative of c0, plus c1, which is the derivative of c1 x minus x0, plus 2x minus x0 epsilon of x. So now if you calculate f prime at the point x0, it will be equal to c1, and this term will go to 0, so it's equal to c1. It means that the existence of finite expansion to the order 1 is equivalent to the existence of the derivative, the first derivative of f at x0, so it's equivalent to the differentiability of f, or of course its extension by continuity if the function is extended by continuity at the point x0. So it's equivalent to the differentiability of f at x0, and it also means that the derivative of f at x0 is equal to the coefficient of the term of order 1 in the expansion. So if you have the expansion to the order 1, you can always conclude immediately that the derivative of f1 exists and it's equal to the coefficient. Now, this is not true for the order 2. So even if you have a finite expansion to the order 2 or greater, it doesn't mean that the function is twice differentiable. if you take, for example, this function and this expansion, you can see that f has a second degree expansion at least, so it has an expansion to the second order plus x2 x sine 1 over x, and this is the epsilon of x that goes to 0 as x tends to 0. So you have this, but this function, if you study it, I will not be doing it right now, but if you do the study, you will find out that this function is not twice differentiable. So the second derivative doesn't exist, even though the second order finite expansion exists. So this remark, if you want, it holds for the first order to calculate the limit, the second order to calculate the derivative, and that's all. Let's now ask the question, can a function f has two different finite expansions, or the finite expansion of a function f is unique? So we have a theorem that says that if a function f has a finite expansion to the order n in the neighborhood of a point x0, then this finite expansion is unique. So to prove it, let's suppose that f has two distinct finite expansions to the order n in the neighborhood of x0. So these two finite expansions will be written as c0 plus c1 x minus x0, etc. And then d0 plus d1 x minus x0, d2 plus x minus x0 squared, etc. Now we might have, of course, c0 equal to d0 and c1 equals to d1, etc. But since the finite expansions are distinct, then at least you should have one coefficient that is not equal to the coefficient facing it of the same rank. So let I be the least rank, the first rank, where ci is different than di. Then if we calculate the difference between the two expansions, all the terms that are equal will vanish, and you will be left with the term ci minus di that will be equal to the difference between the remainders and the higher terms divided by x minus x0 to the power I, which was multiplied by ci minus di. So to see it more clearly, let's say if c2 is and d2 are the least terms that are different, it means that I will rewrite this expansion as c0 plus c1 x minus x0 power 2, power 1, plus c2 x minus x0 power 2, right? Plus I will remove all the terms by writing x minus x0 power 2 times an epsilon 1 of x, which is equal to the remaining terms as I did before. Okay, so as I took a common factor before, and this will be something that goes to 0 when x tends to 0, and I will do the same in the other expansion. So I will be having d0 plus d1 x minus x0 plus d2 x minus x0 squared plus x minus x0 squared times epsilon 2 of x, right? So supposing that c2 and d2 are different, then if we calculate the difference of these two expansions, of course f of x is equal to f of x, so the difference should be 0. Then you will have 0 equals, so I'm calculating in here, so you have 0 is equal to c2 minus d2 times x minus x0 to the power 2 plus x minus x0 to the power 2 times epsilon 1 of x minus epsilon 2 of x. But this epsilon 1 minus epsilon 2, I will call it like big epsilon of x. So the epsilon of x is something that goes to 0. It's not a given function. So we can always use the same notation. We can call them all epsilon of x because it's a representation of a function that goes to 0 and it's not a specific function. So this can be rewritten as c2 minus d2 equals to, I will take this to the other side, it will be minus, I will put the minus within the epsilon, so it will be like epsilon of x times x minus x0 to the power 2 over x minus x0 to the power 2. So I simplify then the x minus x0 power 2, and I will have epsilon of x, which is something that goes to 0 as x tends to 0. It means that if x tends to 0, ci will be equal to di, which is impossible since ci is different than di. That's why, so we cannot have two expansions to the order n of the same function at a point x0. But now the converse is not true, because you can have two expansions of two functions. You can have two equal expansions of two different functions. Like if you take this function and this function, so if you take the first order expansion of the first one, it would be 1 plus 2x plus x times something that goes to 0. And for the second one, it will be 1 plus 2x plus x times something that goes to 0. So you have the same finite expansion to the order 1, but the remainder is not the same, so the functions are not the same. We can also prove that if f is an even function and it has a finite expansion to the order n in the neighborhood of a point x0, which should be equal to 0 in this case, then the regular part of this function, the polynomial part, will be also even. And if f is odd, the regular part will be also odd. And to prove this result, you should write the expansions of f of x and then the expansion of f of minus x, so replacing x by minus x, and then identify them using the last theorem, so using the fact that the same function cannot have two different expansions, so the expansion should be equal, because f of x is equal to f of minus x if the function is even. So try to do this as an exercise. It's nice, it's not difficult. But you must know that the converse is not true. So if you have like this function, let's say, it can be written as f of x equal x2 plus x2. This should be 2 in here, epsilon of x. So this is a finite expansion. The regular part is even, but the function itself, it's not even. Okay? And also, you should know that the finite expansion in the neighborhood of a point x0 can be transferred, can be moved to the neighborhood of 0 by doing a change of variables. So if you perform a change of variables t equal x minus x0, then you can move the finite expansion from the neighborhood of x0 to the neighborhood of 0 and apply the properties and the formulas that you know for the neighborhood of 0. We move now to the next paragraph where we will make the link between the Taylor-Young formulas and the Taylor expansion formulas and the finite expansions. But first, let us state this theorem. It's the term-by-term integration theorem. It says that if f is a function from R into R, differentiable on an interval I, and if its derivative f prime has a finite expansion to the order n in the neighborhood of a point x0, which means that f prime will be written as c0 plus c1 x minus x0 plus etc., and then x minus x0 power n epsilon of x, then f will have a finite expansion to the order n plus 1, so it's one order greater than the order of the finite expansion of f prime in the neighborhood of x0, and we can obtain this finite expansion by integrating the terms of the finite expansion of f prime. So if you have a function with a finite expansion, then the primitive of this function has a finite expansion which is equal to the primitive of the finite expansion itself, so the integral of the polynomial part and the remainder. So when you integrate this, you will have c0 times x minus x0, because you will integrate it between x0 and x, and the integral of f prime will be equal to f of x minus f of x0. So f of x will be in here and f of x0 will come in here, and then you will have this expression for the integral of the finite expansion of f prime. The converse of this theorem is not necessarily true. So if a differentiable function f has a finite expansion to the order n in the neighborhood of 0, it doesn't mean always that its derivative have a finite expansion to the order n minus 1. We take as a counter example this example. So this function has a finite expansion to the order 2 in the neighborhood of 0, because it can be written as 0 plus 0x plus 0x2 plus x2 times x sine 1 over x, which is something that goes to 0 when x tends to 0. So it has a finite expansion and it's differentiable, but its derivative f prime is not differentiable at 0, so it cannot have a finite expansion to the order 1. But you see, so it doesn't work because f prime is not differentiable. But if we know that f prime has a finite expansion of order n minus 1 in the neighborhood of f0, so in this case, if we know that f prime is differentiable, then we can compute its finite expansion by differentiating the finite expansion of f. So I will repeat, if you have a function f that has a finite expansion, then to obtain the finite expansion of f prime, you can differentiate the finite expansion of f, which is the converse of the theorem, only if you already know that f prime has a finite expansion to the order n minus 1. Otherwise, you don't have the right to do it. Now, we can prove the following theorem, which is the most interesting theorem in here. It says that if f is a Cn function, so it's differentiable n times, and then all the derivatives are continuous on I, then f, it has a finite expansion to the order n in the neighborhood of x0, and also the finite expansion is given by the Taylor formula. So it means that if you have a function f that is Cn, then its finite expansion is exactly the Taylor-Young expansion. If f is not Cn, it might have a finite expansion which is not equal to the Taylor-Young expansion. Okay, so the Taylor expansions and the finite expansion are the same thing when f is a Cn function. So now, from now on, we will be dealing with Cn functions, and to calculate the finite expansions, we will be using the Taylor formula. So from now on, the Taylor expansion will be the finite expansion, because we will be dealing only with Cn functions. So let's calculate some finite expansions of some common functions that we know. Take, for example, the function ex. The finite expansion, of course, using the Taylor-Young formula, will be given by 1 plus x plus x2 over 2, etc. So here we are calculating the finite expansion in the neighborhood of 0. So we have the point A is equal to 0. And if we calculate the finite expansion of chx, you should try to do it yourselves. So it will be f of 0 first, so it's 1, ch of 0 is 1, plus you have x minus 0 to the power 1 over factorial 1 times the derivative of sh of ch, which is sh at the point 0, so this is equal to 0. That's why we don't have an x power 1 in here, plus x minus 0 to the power 2 over factorial 2 times the derivative of sh, it's ch at the point 0, which is equal to 1. So we have this term in here, and so on. So we have only the even terms. That's why I will write in here the expansion to the order 2n to represent that we have only the even terms. The same thing can be done for sh cosine x sine x. So shx is equal to x plus x3 over 3 plus etc. You only have the odd terms. Cosine x, you have only the even terms, but you have plus minus as signs of the terms. And for sine x also you have the odd terms with alternating signs, so plus minus. Okay, so these functions and their expansions, you should memorize them, because you should not calculate each time the Taylor-Young formula. You should be able to put them very fast to make your calculations. So you should study these expressions. Now, if you take the function 1 plus x to the power alpha, also you can make some calculations to check it, but we can memorize the finite expansion of 1 plus x power alpha. It's 1 plus alpha x, of course, it's f of 0, so it's 1 plus 0 to the power alpha, which is 1. Then plus the derivative, which is alpha 1 at the point 0, so it's 1 plus 0 power alpha minus 1 times x minus 0 over factorial 1, which will give this term, right? And so on. So try to do it by hand to understand why we wrote this expression. Now if we replace alpha by minus 1, we have the same expansion, but we replace alpha only by minus 1, so it will 1 over 1 plus x, so it will be written as 1 minus x plus x2 minus x3, which is the expression that we started with in the beginning of the chapter, plus xn epsilon of x, of course. And if we apply the change of variables x to minus x, we replace x by minus x, we'll obtain also the same formula that we had in the beginning of the chapter for 1 over 1 minus x. Now if we integrate 1 over 1 minus x and 1 over 1 plus x, we can have the finite expansion of the logarithm. Of course, this is done using the theorem of the integration of the finite expansion. Then if we integrate 1 over 1 plus x between x0 and x, we will have ln of 1 plus x minus ln of 1 plus 0 that I will take to the other side, so it's equal to ln of 1 plus 0, which is ln of 1, so it's equal to 0, plus the first term of the expression 1 over 1 plus x was 1, so integrating 1 between x and x0, it will give x, and so on. So you will have this expression for ln of 1 plus x. Of course, I repeat that you should try to do it by yourselves to practice a little bit how we are calculating them. And also an interesting example that we should know is the case of alpha equals to 1 over 2, which means that 1 plus x to the power alpha will be 1 plus x, or square root of 1 plus x. So using the formula that we have in here, okay, replacing alpha by half, we will have 1 plus half x minus 1 over 8 x2 plus x2 epsilon of x, if we calculate the expansion to the power to the order 2.